In this video, we'll be talking about systems of linear differential equations. You will remember that we have recently talked about differential equations. There were equations of basically the form y prime of t equals y of t plus possibly some inhomogeneous term. Now we're going to talk about systems of equations of that kind. So let's start with defining what we actually mean by that. This is section 11.2, systems of linear differential equations. And we'll start with a definition. In this section, we'll only talk about homogeneous systems, so we will not have any inhomogeneous right-hand side terms in here. So let's define what that is. A homogeneous system of linear differential equations with constant coefficients that is a system of the form, and that looks like this: y1 prime, y2 prime, and so on up to yn prime is equal a matrix A times the functions y1 of t, y2 of t, and so on up to yn of t. Plus we have initial values, so usually we have values for the point 0, so y1 of 0, y2 of 0, and so on up to yn of 0 equals some given constants, gamma 1, gamma 2, up to gamma n. Where A is a matrix in R n times n, and the vector gamma 1 to gamma n is also a vector of reals. So we only have terms involving y and y prime. This means the system is homogeneous. And we have constant coefficients, meaning this matrix A here is constant. So that does not depend on t. To see how systems like this work, we'll consider an example first. So let's see an example here. I'm trying to keep things deliberately simple, so of course this example is simplified a little, just to illustrate the phenomena that we'll have to deal with here. Okay, so we'll consider an example from biology, biological systems. Specifically, we'll consider squirrels and raccoons. These squirrels and raccoons are competing for the resources in the same environment. So, for example, they compete for food, they compete for water, and so on. So the growth of their respective populations depends not only on the population size of their own population, but also on the size of the competing population. Obviously, if the number of raccoons grows quickly, there is less food for the squirrels, so the number of squirrels grows less quickly. Okay, so squirrels and raccoons are competing for the same resources. Think things like food, water, area, etc. Their population growth depends on the size of their own population and on that of their respective competitors. Specifically, we can express this as two differential equations, and we do this by denoting by R of t the number of raccoons at a time t, and by S of t the number of squirrels at time t. And then we have differential equations that govern the growth rates. So let's assume for the growth rates of raccoons and squirrels, we have the following differential equations. R prime of t, so that's the growth of the raccoon population at time t, is 5 over 2 times the current population size, R of t, minus the size of the squirrel population, S of t. And similarly for S, the growth rate S prime of t depends negatively on the raccoons. So let's say this is minus 1 over 4, the current raccoon population, plus 5 over 2, the current squirrel population. So the question is, given some initial values for these two populations, how will they evolve over time? Will there be something like a natural balance between the number of raccoons and squirrels? Will that converge to some numbers? Or will one of the two species possibly die out? Or will one of them explode and the other will be small? All of that is possible, and we'll have to find out by solving this system of differential equations. So to get an actual solution, let's assume some initial populations as well. So assume initial populations. Let's say the number of raccoons at time 0 is 60, and the number of squirrels at time 0 is also 60. So the question is, how do we solve this system of differential equations? You can imagine that is not that easy. I mean, both of the equations involve both functions r and t, so it's probably not that straightforward to solve it as it was before with just one function, one equation. So the main idea here is, of course, to build on what we already know. And that means If both of these equations only involve one function, then we could solve them independently. Would basically be the case that we already know how to do it. Okay? Well, that would be the case if the matrix A governing these equations was diagonal. Okay? It's obviously not the case here. But let's have a look at that idea first. So, if A is a diagonal matrix, then each row is a differential equation that is independent of the others, and that means we can just solve each of these rows separately. Such a state where each of the rows are independent from each other, so where A is a diagonal matrix, that would be called a decoupled system. Now let's see how that looks like. If we have a system that looks like this here, so y1 prime of t, y2 prime of t equals lambda 1, 0, 0, lambda 2, for some values of lambda 1, lambda 2, y1 of t, y2 of t. Then obviously we could solve both of these equations on its own. So we will get solutions y1 of t equals some constant gamma 1 e to the lambda 1 t, and y2 of t equals gamma 2 e to the lambda 2 t. Okay, so that would be easy to solve. So the question is, can we somehow achieve a form that looks like this? Can we decouple a system? And from linear algebra, you already know that there are, in fact, methods to decouple a system. They don't work in every case, but they work in many cases. And we'll investigate that idea a little more in the next section. But let's first sketch how this will work out for our systems of linear differential equations. So, if the system is not decoupled, let's say we have a coupled system, what are we going to do then? What we would like to have is, we would like to find a basis for that matrix A and then do a basis transformation such that the resulting matrix is a decoupled system. So the resulting matrix is a diagonal matrix. Then we could solve the differential equation system in the new coordinate system. And after that, we could just transform the solutions back to the old coordinate system. And we have our solution. That's basically the idea. So what do? Well, we need a basis and a corresponding basis transformation. We call that S, the transformation matrix. That's square n by n matrix. And it's invertible because it's a basis transformation. Such that, well, the transformed matrix, that is S to the minus 1 AS. So that's the matrix A converted to the new coordinate system represented by S. And this matrix, we want that to be diagonal. right? If we have that, then we could do the following. We do substitution. We just substitute and say we substitute like this: y equals sc for some new set of function c. And that means, conversely, c equals s to the minus 1 y. Remember, s is invertible, so we can actually do that. That means the differential equation system y prime equals a y. What would that be then? Well, y is s c prime, so we will get s c prime equals a y, and again y is s c, so we get ASC. We could slightly transform that by simply multiplying this with the inverse of f from the left, and we get c prime equals s to the minus 1 ASC. So that's exactly DC. And remember that matrix D, that was diagonal, so we have a decoupled system. And we know how to solve that. So what we do then is solve the new decoupled system, and after we did that, transform the solution back through our substitution. You remember that y equals SC, so that's exactly what we do then. Yeah, we take the solution C that we computed and transform it by multiplying S times C. That gives us the solution Y to the original system. Okay, that's all a little abstract probably. So let's see an example of how this works. We get back to our squirrels and raccoons. Remember that here, that was the system. Let me just copy that. Okay, so that was our squirrels and raccoons system. Now let's formulate that in terms of a matrix first. That's easy. So for the matrix form, what we do is pretty much we take R and S and say, well, R prime, S prime, I'll just leave out the T to have that in a more concise form. So we say R prime, S prime equals some matrix times the vector RS. Again, I'll leave out the T. And the matrix, well, that looks like this. We have 5 over 2. We have minus 1, and in the second row we have minus 1 over 4 and 5 over 2 again. Okay, so this here, this is our matrix A. And we want to decouple that system. Now, we have not yet talked about how to find that basis transformation S that we need. So for the time being, I'll just tell you how it looks like. So we're going to use S as the following: minus 2, 2, 1, 1. And from that, we can easily compute the inverse of S, that is minus 1 over 4, 1, minus 1, minus 2, minus 2. And if we have these, we can compute S to the minus 1 AS. If you do that, and I recommend you do, just for practice, then what you get is the following matrix: 3, 0, 0, 2. So we do indeed get a diagonal matrix. So that is the transformation that we wanted. Now, having this diagonal matrix, we can now solve the transformed system. And the transformed system is C prime equals dC. And again, D is 3002. So the solution that we get is C1 of t equals a constant gamma 1 e to the 3t, and C2 of t equals a constant gamma 2 e to the 2t. So all we have to do is we have to transform back. Remember our substitution. Let's go back to that. So what we did is we substitute like this here. So specifically, we have y equals sc. So our original solution equals s times the solution in the new coordinates. And for us, what that means is our solution Rs is equal to S times C. S, that was the matrix minus 2, 2, 1, 1, times gamma 1 e to the 3t, gamma 2 e to the 2t. So what we get here is the raccoon population is a function of the form minus 2 gamma 1 e to the 3t plus 2 gamma 2 e to the 2t. And the squirrel population is a function of the form s of t equals gamma 1 e to the 3t plus gamma 2 e to the 2t. And now finally, what is left is to determine these constants, gamma 1 and gamma 2. And we can do this by using the initial values. Remember, the initial values were R of 0 is 60 and S of 0 is also 60. So if you substitute that into our solution, then we get R of 0 equals, well, that's minus 2 gamma 1 plus 2 gamma 2. That's supposed to be 60. And S of 0 equals gamma 1 plus gamma 2. And that is supposed to be 60 as well. And if we solve this system of linear equations for gamma 1 and gamma 2, what we get is gamma 1 equals 15 and gamma 2 equals 45. So the solution that we have at the end is R of t equals minus 30 e to the 3t plus 90 e to the 2t. And S of t equals 15 e to the 3t plus 45 e to the 2t. Okay, so this is the solution for our system of linear differential equations here. Now, if we investigate that a little closer, the question was, can we find out how the population behaves in the long term? And if we have a look at that, then we can indeed find that out. Here's a graph, a chart, where you can see the two functions plotted. And you can see how the number of raccoons and squirrels behaves in the long term. And it's easy to see that the squirrels far outnumber the raccoons by some point. The raccoon curve even goes into the negative, which of course it will not do. It will stop at 0. And of course, from that point on, the growth of the squirrels will also be different. But you can see the squirrels are winning and the raccoons are dying out in that simplified model. Okay, so that's basically how you solve linear differential equations with constant coefficients. That leaves us, of course, with one major question, and that is, how do I get this basis transformation, and under which conditions does that even exist? In this example, I just gave that to you, but of course, there must be a way to compute that or to find out whether there exists a basis transformation like that. And that is what we're going to deal with in the next few videos.